Okay, that's okay. Right, so thanks a lot for allowing me to speak here and for actually, in fact, squeezing me into the already busy schedule here. So this is actually, I'm really a physicist in exile, okay? So this is actually not a very mathematical talk, probably. Yeah, I was gonna say that while at home the MPs take over the Commons to decide on a very difficult question and try to solve a very, very difficult problem, I'd like to tell you a bit about a much simpler problem. This isn't working. I think we've exhausted the. No, it's working. Sorry, switching on helps. About dynamics of Gaussian states in open quantum systems, in particular, two simple types of open quantum systems described by non-Hermitian operators and by Lindblad equations, and they are related to each other. So all of that is joint work with Roman Schubert in Bristol, who I think at some point was thinking of coming here too, but is apparently too tied up with all sorts of looking after students in Bristol. And with two of our PhD students, Bradley with me in London, and Tom in Bristol with Roman. Right, so to set the scene, I always like to start out with telling people what I mean when I say this quantum classical thing, okay? So you're all very well aware of this. When I say classical dynamics, I don't have anything else in mind but Hamilton's equations of motion. If I say quantum dynamics, what I usually mean is Schrödinger's dynamics. You will see later that in this Lindblad thing I talk about mixed states as well, so it will be slightly different. And as you know, these two are connected in various ways. It's not as simple as one might have imagined or hoped for in the very early days of quantum mechanics. So I guess people did find it a bit of a disappointment that this limit of h bar going to 0 is not a very simple limit, but a singular limit. But of course, we do know, all of you guys know very well how to handle these limits and how to go from here to here and backwards. And my favorite way of doing that is actually to use Gaussian wave packets. And I think I share that with some of you here as well, but also with some of our speakers for tomorrow who haven't, I think, made it here just yet. Anyway, so just a brief sort of setting the scene again of what I like about this. You know? So as you all know, when you do a time evolution of a Gaussian wave packet, then in a semiclassical limit, you obtain Hamilton's equations of motion for the center of it. But you can also then use these Gaussian wave packets in various ways to go back to quantum mechanics. And you know, all these sort of tools we like and use, trace formulas, quasimodes, semiclassical propagators, they can all be formulated in terms of coherent states or Gaussian wave packets. I know there are many other ways of viewing them too, but most of them were formulated that way, one way or the other as well. So they can be a very sort of useful tool for this. Now what I'm interested in is open quantum systems most of the time. In fact, I just give you a very brief overview now. I'm going to give you a more detailed overview in a few minutes. So there are basically two types that I'm interested in that are, in some ways you can view them as toy models, but I'll show you later some examples where they describe reality quite well. So one of them is non-Hermitian Hamiltonians, where you actually use a complex energy to describe decaying states, or you know, in many systems, resonant states, which is a pure state description where probability but also energy aren't conserved in the system. There's another thing that I'm interested in, which is a Lindblad dynamics for density equation, density operators. So what you talk about there is mixed states, and in these systems you can describe measurement, finite temperature effects, loss of particles in many particle systems and other things. And here the probability is conserved, so it's quite different from these non-Hermitian ones where we encode losses in a loss of probability. But you don't have a pure state anymore in exchange, okay? So the thing I'm interested in is somehow I'd like to have some more semi-classical methods for this. So there are several people who've been looking into semi-classical methods for open systems, but it's still nowhere near as many as are interested in that for closed systems, of course. And we have a much, much smaller toolbox. And as I've been saying, I'd like to use the toolbox of coherent states in particular to apply them to these things. So to give you a brief outline, I first want to motivate a little more about what non-Hermitian Hamiltonians are and Lindblad equations, because not all of you might use them. Probably many of you don't use them. Then I'm having a brief reminder about Gaussian wave packets and semiclassics, so that is probably very familiar to most of you, but there might be sort of an angle of view which you might not normally adopt, so I do want to definitely not jump over that, but let's set that in there. And then I actually come to the main topic, so that's the semiclassical limit for the Schrödinger dynamics with non-Hermitian Hamiltonians, where we recover dissipative phase space dynamics, which is also having a metric and not just a normal phase space where we usually ignore the metric. And I also show you an application of this for light propagation in absorbing media. Okay, and then finally I do the same thing again for Lindblad dynamics, where I get a different dissipative phase space dynamics. And I also show, I will compare them very briefly. There's not enough time to compare them completely. If Roman had made it here, we could have had one talk on this and one on this, and we could have compared. But this way, I just make some comments on it. And then I show you an application again of cold atoms with losses, and some of that without the losses will probably link nicely into some of the things discussed later in the afternoon today. Right. So let's start with non-Hermitian and Lindblad systems. Just a bit of a motivation. I think I might stand here. It's better. Sorry. Right. So non-Hermitian physics. So obviously in quantum mechanics we usually demand the Hamiltonian to be Hermitian, and that's to guarantee real eigenvalues, unitary time evolution, and yeah, that's basically it. Orthogonal eigenvectors, but that's in the unitary time evolution. Of course, if you don't want this sort of energy and probability conservation, then the simplest way to describe something that decays in time is actually to encode it in the probability to be there. Okay, so if you take something, the probability of it being there decays exponentially, you can think of that as an exponential decay, and that's encoded in an imaginary part of the energy. And Gamow, as many of you know, used that very early on in quantum mechanics already. So you need to keep these time frames in mind. You know, Schrödinger, of course, had only just written down his equation, right? And already then people started thinking about what if we make a complex energy in there, can't we describe a decay with this? So this is sort of one of the motivations for non-Hermitian systems, but I do feel I should mention PT-symmetric quantum theories as well here, because many of you might have encountered that, often even equated with the term non-Hermitian, which is originally quite a different motivation of considering non-Hermitian Hamiltonians, and that was the idea that if a Hamiltonian still has real eigenvalues, a completely real spectrum, which, you know, nothing prevents it from doing that, just because it's not Hermitian, then perhaps one could have a theory of closed quantum systems. So that's how this field started out. But in the meantime, really, all the applications of that field are actually in open systems where you have gain and loss, but in somewhat balanced way. So for me, PT symmetry is just a special case of this sort of idea. But we don't only have decaying modes, we also have growing modes. But to be honest, you know, I am in a math department after all. So basically from now on, we're mostly concerned just with saying, well, what if we do have a Schrödinger equation and the Hamiltonian in it is just not Hermitian, what happens? Okay, you know, no matter where it came from, whether it came from here or from any other place. And of course, you can always write it as a Hermitian and anti-Hermitian part. Right, so a few more words about PT symmetry. So originally this symmetry was viewed as parity and time reversal symmetry. So that was the first examples people looked at. So that's the name PT symmetry for you. But in the meantime, it's actually been sort of appreciated that there's much more general symmetry ideas there, that a general anti-unitary symmetry can lead a Hamiltonian to have purely real eigenvalues. Okay, and that's sort of where things get interesting. But it can also, the Hamiltonian could also have complex conjugate eigenvalues, and that's often viewed as the PT broken phase. And that's actually where a lot of interest in experiments lies at the moment. But before going to technical here, let me just give you this very simple example of a two-level system where we have one level with a growth in the probability and one with an exponential decay. and they're coupled with this coupling strength V. So you can think of lots of physical setups. I'll show you one in a minute, but it's just two levels coupled with that strength. And you can see that the eigenvalues are purely real as long as the gamma, this decay rate and growth rate, is smaller in magnitude than the coupling between the two states, right? And the symmetry in this one here is simply the interchange of the levels. That would be your parity. And the time reversal here is really simply just the complex conjugation. So physically, you could also view it as changing loss and gain. Okay? And you could also view it slightly differently and say the symmetry here is actually physically a balance of loss and gain. So I have the same growth rate in the one state, the loss rate in the other, and the system otherwise is symmetric. So that's your PT symmetry in this example. So this one, as I said, can be realized in many different ways. And one which is quite nice, it's not quantum, it's classical optics, is actually to use the analogy between the time-dependent Schrödinger equation and the 2D propagation equation for optical waves in a paraxial approximation, but don't worry too much about the details here. So the idea is that this Hamiltonian here could be realized in two coupled optical waveguides, where one of the waveguides has gain, the other one has loss, and because they're close to each other, they have an evanescent wave coupling. It's a 2x2 matrix here because these would, in that case, be single mode waveguides. They only fit one single mode. Okay? You can actually look at a slightly simpler system experimentally if you wish, because loss always comes for free in these experiments. Gain is something you can realize, but you have to work hard for. For example, you can laser pump the system, then you can do a gain. But the loss is very simple, and you can see it's just an overall imaginary shift of the energy. So the Hamiltonian properties aren't really changed very much. You just get an overall extra decay rate. Okay? So this waveguide system, what we're going to do now is we put light into this upper waveguide, and we see what happens as it propagates. So here in false colors, I show you what happens if there's no absorption. So this is the familiar, whatever you want to call them. I tend to think of them as Rabi oscillations from atomic physics analogy, but they're just oscillations between these two coupled states. So where it's red, there's a lot of light. Where there's blue, there's no light. It just goes back and forth. So now if you put loss into this lower one, at first it seems that there's not much changing, right? It still just oscillates back and forth, but it's damped overall. You know, there's dissipation on top of it. But that's not the whole story. So I could show you lots more pictures here of what actually happens when I increase the gain. But let me show you just summarizing things in one quantity to look at. So let's look at what happens to the overall transmission of this. So you put light into this, and you ask how much light comes out at the end of the structure. Obviously, that will depend a little bit on how long the structure is, but the curve we get is pretty universal. So transmission as a function of loss. So what you do, you can do that obviously numerically, well, analytically actually really quickly. It's a 2x2 system. You can also do it in the lab. So let me show you the results of this paper by Guo and others from 2009. So it was Christodoulidis and others who actually implemented these things in a two optical waveguide system. And the theory and experiment are here. So what you observe is that intuitively you'd probably think that if you increase the loss, there's less going through the structure. And for small loss rate, that's indeed true, right? But then if you increase the loss further, there's actually more coming out of the structure than for smaller losses. Okay? And that sort of is, depending on you put it, it might be a bit of a counterintuitive effect. Obviously, it's easily explained analytically with these things here. But this effect and others, I think, have really convinced people in optics that non-Hermitian systems aren't just like Hermitian ones with a bit of extra decay, but they can give us completely new features and tools, and that we don't only have to use them just as a brake like here in the car, right? We do use dissipation for these things, but we can also use them for other things. So particular features like this make people think of switches and diodes and so forth, and they've built all sorts of things with it. Right, so there's been quite a lot of interest in these PT-symmetric systems, and they have luckily sort of then also amplified the interest in non-Hermitian systems as such. Right? So as I said, this is really just, PT is just an example for me, but it still has interesting properties sometimes. For this here, we clearly do not need semiclassics, but for more complicated systems, we do. Right, so that was non-Hermitian ones. So how about Lindblad? It's a completely different world, actually. So what we're looking at here is the evolution of a mixed state. So if there's no environment, a mixed state evolves according to the von Neumann equation. So you know, this is the unitary dynamics. And now, if you couple your system weakly to a bath, that's the physicist view in some ways, or the mathematician view is what's the most general equation that would still preserve most properties of quantum mechanics for you while not being just unitary. You get the Lindblad equation here, where you have these operators L, K, which represent some sort of dissipation from the outside, or some, if you want to, they represent your environment and the coupling to it. And you can model all sorts of things with it, measurements, finite temperature, or as I said, losses of particles, and so forth. Okay. So losses of particles is actually some example that I will show you later, and that's actually kind of closely related to this idea we saw before, that when you describe a complex energy, use a complex energy to describe decay, right? So that's sort of saying a particle is lost out of a particular system. So Lindblad, you could do the same. So here we work in a second quantized picture. So what we do is, if you want to destroy particles or lose particles out of a particular mode, the Lindblad operator, which now I wrote as this curly L here, would be the annihilation operator for particles in that mode. That sort of is intuitively, it does make sense, you know, you're losing particle out of that mode, so you're destroying particles in there. And if you do look into what just the Lindblad part does for a single mode, then indeed you see that the expectation value of the particle number goes down exponentially if you have this Lindblad dynamics. Okay, so this is how you can model an exponential decay of particles in a Lindblad formalism. But here, remember, the norm of that state stays constant all the time. Right, and here's an example. You can't actually see it so nicely, but you can see the Schrödinger equation is being etched into a lattice of cold atoms here in the lab of Herwig Ott in Kaiserslautern, where they actually implement controlled single particle losses in cold atoms in an optical trap. So you can control it experimentally, but it's quite a challenge to describe such a thing numerically. Theoretically, no way. Numerically, no, you can't do that either. So there's no one, even without the losses, there's no one who can describe more than this bit, for example. Okay? We hear a bit more about the challenges of this later in the afternoon, I believe. Right, so there is some motivation into why we look into these things. Right, so there is a connection between Lindblad and non-Hermitian physics, obviously. There are many connections, so let me just point out one of them. So one of them is what's known as the quantum jump approach to Lindblad equation. And that's, if you view the Lindblad equation the same way I wrote it down before, you have the Hermitian evolution here, or the unitary evolution. Then you could view this bit here just as an extra anti-Hermitian part in your Hamiltonian, right? So this, if you just add that to the Hamiltonian and put them together, you could write it like this, where H now is H minus I L dagger L. The sum over all these L dagger L's. But then you have one term left, which is then usually viewed as the so-called jump term. And numerically, what one does is this quantum jump approach, or sometimes called quantum trajectories, is you can also take this equation and you, instead of solving this one deterministic equation, you can write it as an average over pure state stochastic equations. And the idea here is that you can evolve a pure state with this effective non-Hermitian Hamiltonian, H minus I L dagger L, for certain periods. The norm will decay in that time, and proportionally to the norm, you get a probability of getting a quantum jump, which brings it back to unit norm. Okay? So it's a sort of non-Hermitian dynamics interrupted by stochastic jumps. Okay? So this is one way they're related, and obviously this non-Hermitian Hamiltonian does contain information about the full dynamics in this. In fact, one could argue it morally actually contains all the information, because it even encodes the probability of the jump as well. Right? So they are very closely related. There are other ways in which they're related, but I don't want to dwell into this. right now. Okay, so with this in mind, let's shift gears and go to a completely different subject. That's these Gaussian states and how you do semiclassics with them. That's just a reminder, very brief reminder. So I don't know why I wanted to fill up this slide. I think all of you know what the Wigner function is, but never mind. So we look at the Gaussian Wigner function here, which in this case we do think of mixed states as well, because we already have in mind that we might do Lindblad later. Okay, mixed states or pure states. There's a picture here of the Wigner function of the Gaussian when this covariance matrix here is the identity matrix. That's what people usually refer to as Glauber coherent states. G is always a positive symmetric matrix, and this Wigner function here represents a pure state if and only if the determinant of G is 1. Okay? So this can be Gaussian, whether it's pure or not. Okay? So you can have a pure state which looks like a Gaussian in phase space. You can have a mixed state that looks like a Gaussian phase space, but it's in the determinant of G which one you have there. Okay? So the nice thing about Gaussian states, there are many nice things about them, but one thing is that, of course, if you evaluate the expectation value of any operator in such a Gaussian state to leading order in H bar, you get just whichever classical symbol you want to associate to it at the center of the Gaussian. Okay? And it doesn't matter which one you choose because they all differ by orders of H bar, and that's only the leading order of H bar. So you basically take the hat of the operator, you evaluate it at the center, and that's your classical phase space function. And let me mention, though, that the uncertainties and all the covariances are encoded in this covariance matrix G of the Gaussian. Okay? So this is where the view is perhaps a little different from what one usually has in mind. So yes, Gaussian states do go to phase space points when H bar goes to 0, because this just gets more and more localized in phase space, and these corrections get smaller. So you basically just end up with a point. But it does have a shape. Okay? It does know about its orientation in phase space. And in the non-Hermitian context, I tend to think of it as a metric, as you will see in a moment. But in the Lindblad one, I have to be a bit careful, but at least it has a sense of distances and directions. Okay? So if it's long stretched in one direction, even when it shrinks to a point, this is still going to be important. And one tends to not think about it too much in unitary evolution, because it never really influences what happens. But, I mean, we've seen in Frank Grossmann's talk yesterday, was it yesterday? The day before, I'm already mixing up the days, the nice review of Heller's method of thought Gaussian wave packets, where in fact, often we do take this shape into account. Yes? It's a Wigner function, but it looks the same as a, yeah. It looks, I mean, the Hosimi function of a Gaussian state would look also like a Gaussian, but it's a bit broader than the Wigner function. But for Gaussians, they are almost the same. And I believe everything we've done here, you probably could do with Hosimis as well. But we've chosen to do it with Wigner functions. Yeah? So it's the Wigner, and with Hosimis, I'm not quite sure what happens for mixed states, how nicely these things go through. I haven't done it, so. Yeah. Yeah, it would look the same, but there's some sort of, this G here wouldn't be determinant 1. Yeah, so the G wouldn't have determinant 1, but 1/2 then, I guess. So that's what would make the difference for a pure state. But it, for Gaussians, they're pretty much the same. Right? So the same arguments would hold. Right. Okay, so let me just sort of briefly reiterate how we get from Gaussian states to classical dynamics. So has been worked out in much more detail by Hap, Heller, Littlejohn, others in the 1970s. You use the idea that a Gaussian stays Gaussian under a quadratic Hamiltonian. And then, of course, if your real Hamiltonian isn't quadratic, you Taylor expand it around the center of a Gaussian. So, I mean, there's sort of these two things go hand in hand. One can't do one first and then the other. Right? So you have to assume that your state is Gaussian to start with. It doesn't have to be Gaussian, but it's very well localized, right, of order H bar. And with that argument, you can see I can Taylor expand my Hamiltonian because it doesn't actually see much of what happens where the Gaussian is almost zero, right? But if that's the case, then you can, again, put an ansatz for the time-evolved state to also be Gaussian, because under quadratic Hamiltonian it would be Gaussian. You do that consistently, and you get the semiclassical evolution. I didn't actually mention what the Z was. Yeah, sorry. So the Z just encompasses Q and P variables. So it's both Q and P just in one variable to save a bit of space. And you just get, for the central motion, you just get the Hamilton's equations, but we shouldn't forget about the fact that this matrix G also, the covariance also moves in time. In this case here, it's just the linearized flow of the classical dynamics. So you could argue this is actually contained in this, because if we know the classical flow and the linearized flow, we get both of these. And just sort of a little example of a Gaussian moving in an anharmonic oscillator. Here's the quantum evolution and the Wigner functions. Here it's nice we pick the weakness, because you can see where it's getting dark. Here we actually get some interference effects. And in comparison is what a Gaussian would do according to this here. So the Gaussian tries to follow the trajectory, and it tries to mimic this reshaping of the actual Wigner function, but of course it can't. It's a Gaussian, right? So it can't actually bend around. And as soon as this guy here gets a bit too long, this is nice. We have this sort of error control in here. If that gets too long, then the Taylor expansion will break down, and our classical approximation or Gaussian approximation isn't good anymore. That's when quantum mechanics happens, which is nice. Yeah? We like quantum mechanics as well, don't we? And of course, there are ways to take lots of these guys here, as we heard in various talks already, for example, with lots of different methods, for example, these coupled coherent state methods, and put them back together to get the exact quantum dynamics. Right, but we're not actually going to go that far. We're just going to try to do the same thing now with a non-Hermitian Hamiltonian. So that's something Roman and I have actually been working on already a few years ago. Yeah, it's quite a while ago by now, where we just take the Schrödinger equation with a non-Hermitian Hamiltonian. We write it as Hermitian and anti-Hermitian part. You can always do that. In the phase space, it's just the real and imaginary part of the Hamiltonian function. Again, Gaussians stay Gaussian. Actually, they don't care if the Hamiltonian is quadratic. They don't care whether it's complex or not. They will stay Gaussian. So we make a Gaussian ansatz for the time-evolved state. We Taylor expand it around the center of the Gaussian, and we get a new phase-space dynamics, which looks like this. So I actually wrote it down explicitly for you here. I should have maybe folded it all up in a matrix equation, but here you can see it sort of nicely. You get Hamilton's equations here. And now I've actually chosen to write down the actual covariance matrix, which is 1 over this G, so you don't get funny to the -1s here. So you see how the covariances now couple to the derivatives or the gradient in the imaginary part of the Hamilton function. And these are the covariances, but they move as well, of course. And this is not quite the linearized flow anymore, because one has to be careful with, I think the linearized flow could in principle violate uncertainty relations. So that's been taken care of here automatically. That doesn't happen. Yes? No, no, it's here. So the H here is HR minus I, HI. They're real now. Yes. They're real because they're the expectation values of the Gaussian. So they're the real center of the Gaussian. There's been quite a few nice things about this here, because one could, of course, look formally at Gaussians with complex centers. But as we know, there's always one Gaussian with a real center which corresponds to many Gaussians with formally complex centers. And this here is how the real Gaussian center moves. But it's an equation where, in fact, the dynamics of this covariance couples back into the dynamics of P and Q. It's quite different from how it is in the unitary case. And just for completeness, you can then, of course, eventually get the total. You also have the norm decaying, which you then describe. In addition, once you've integrated these equations, you get the equation for the norm out. So just sort of a pictorial interpretation of this, you can think of this flow here as the real part of the Hamiltonian just giving you a symplectic flow which conserves energy as we know it. But this part is actually even simpler. It's a gradient flow, and it follows the sigma here, or this G. This is why I tend to think of it as a metric here. It tells you what's the fastest way to get to this minimum of hi. Okay? So this flow here just tries to minimize the function hi. And in some ways you could view that, and some people have made these observations out of completely different motivations. You could think of that as a classical flow where this here is the energy of a system and this here is minus the entropy of a system. So people have been thinking about this in other contexts. But what we have in addition is that this sigma matrix now changes in time. So what's the fastest route to the minimum of hi actually changes over time. Right, let me show you an application of that. So again, we look into optics. So here I actually wrote it down for you. So the propagation of the electric field amplitude of an optical wave in 2D in one direction here, in this paraxial approximation, which basically said not too much is varying in this z direction, looks very much like the Schrödinger equation. Of course, I already written it for you like the Schrödinger equation, where you have some wavelength here, which gives you the h bar, and a potential, which is really the refractive index variation of your optical medium. So if you have a complex refractive index, you can use that to model amplification and absorption in classical optics. You know, this is not quantum optics. And that actually is a realization of a non-Hermitian Schrödinger dynamics. So what one does here, so I just go through that again, because it looks a bit different in this context. You take an initial Gaussian beam, you make this ansatz, and the equations of motion simplify a little bit here. So because your Hamiltonian is of the form p squared plus v of q. And what you see here again, you get sort of the standard beam dynamics, which is Hamilton's equations, and then you get this width parameter of this Gaussian shape coupling back onto this imaginary part of the potential. Just to show you an example, we've been looking at a model of a very deep waveguide structure. So this blue one here is the actual confining potential of the waveguide, and in pink I show you an absorption structure. So we assume that this is PT-symmetric in fact, but it doesn't have to be, but it is PT-symmetric, where there's a gain on one side and loss on the other side of the structure, and I amplified that by a factor of 10 so you can actually see it. So we actually really have quite a small loss here, depending obviously what the gamma is, but that's for the examples we look at now. And we put in this of parameter eta so we can make the system more or less semi-classical, basically. So in comparison to the ground state of this, if the eta is large, the potential varies quite slowly, and we expect things to move according to classical dynamics. Well, the new classical dynamics. So here's just some pictures of the quantum and the classical evolution, and you can indeed see for the examples that as this parameter gets bigger, the quantum and classical evolution look more alike, but you could argue they also look a bit more boring, but that's just a matter of initial conditions. So here's another one for 15 where you see there is non-trivial beam dynamics going on here, but they look the same for quantum and classical dynamics. Okay, obviously it's made like that. So if you make the potential much narrower, this is not going to work as you saw here. There are quantum effects coming in. So one thing that I've been just telling you about is that there's the beam width actually now enters the dynamics of its center. So let me just show you that in a very simple example. So if we don't have absorption in our system, we put a beam close to the center of this trap, and it's almost harmonic, so it just oscillates back and forth in a harmonic way. And it doesn't actually matter how broad the beam is. That's the whole idea about beam dynamics, that it doesn't matter how broad it is, it has the same central motion. It changes its shape, obviously, but the central motion is the same. So of course, that's not the same anymore with absorption. So if we take an example where we put some absorption in, we can put a beam in the middle such that it actually just sits there. So it actually does have an initial momentum to counterbalance from the pull from this gain region. But if you make it broader, it starts oscillating in one direction. If you make it narrower, it oscillates completely different in the other direction. And this is completely classical dynamics. So the classics and the quantum one do agree. There's no discrepancy of them. They're actually exact because it's harmonic in this bottom. And still, you cannot get rid of the shape in the classical limit. Okay? So even when it goes to 0, it's still there for the absorption. And we do think that's probably something one can actually probably used in experiments for something. I'm not very applicationally minded, so I'm not sure, but it seems nice that you can sort of, if it's broader, it goes one way, if it's narrower, it goes the other way. It's like a prism for width or something. Don't know whether anyone needs that. But it's an interesting effect. So I don't have that much time left, so I need to get to the Lindblad dynamics now. Right, so we do the same for Lindblad. So again, a shift of gears. But as I said before, they're kind of related. So it just sort of, to reiterate, this is the equation we're looking at now, and we're interested in the dynamics of Gaussian states. So this is probably the right point to say, perhaps I should have said it much earlier, that one of our organizers, and Olivier Paudet, who's also in the audience, of course, have studied similar questions before in a series of very nice, but also quite technical papers with, as you will see, if you know them, it's perhaps slightly different point of view again, okay? But there has been interest in that before, and also many results. So we're going to follow straight the method we've been talking about. So what we need to do is now we write the Lindblad dynamics for the Wigner function in phase space. This is just how it looks like. And now, again, Gaussian Wigner functions actually do stay Gaussian if the Hamiltonian is quadratic, and the Lindblad operator now is linear, okay? So what we do now is we make a Gaussian ansatz, and we again need to Taylor expand. So there are subtleties in here. I won't go into the subtleties, but there are different orders to which you have to expand Lindblads in the different parts of the phase space equation so that you're consistent with getting everything up to order h bar. If you do it right, well, what we believe is right, at least, you end up with these equations of motion for the center of the Gaussian and this shape parameter, the covariance. The center here has, again, the Hamiltonian bit, and then the Lindblad bits give you this additional structure here. Note that this actually looks quite different from the non-Hermitian, but I come to that in a second. And the metric here also changes. It's not a metric actually anymore, sorry. So this here obviously won't stay determinant 1. I forgot to mention that. In the non-Hermitian one, the G actually does stay of determinant 1. It's conserved automatically. So the state doesn't all of a sudden shrink down to a point violating uncertainty relation. But here it can change. It can get broader, which would indicate a mixed state, of course. And there are various terms hidden in here which are all vaguely to do with linearized dynamics again. So the center, again, is a generalized flow, and let me come back to that. And the covariance is basically linearized, but there are, again, quantum corrections protecting this uncertainty thing. Because otherwise, if you just evolve a classical flow with this and linearize, it would violate uncertainty principle sometimes. But this automatically protects it. It doesn't do that. So the Lindblad term here now, what we were interested in a bit as well, is what's actually a structure of that. What is this guy? And it turns out sometimes it's actually a gradient flow, which looks a bit like the non-Hermitian one. Sometimes it's actually a Hamiltonian flow, and sometimes it's neither. Okay, so it really depends. So it turns out that when the Lindblad operator is an analytic function of the phase space variables, so of Q plus IP or Q minus IP, then in fact it's really just the gradient of this function L dagger L, which actually appeared in our effective non-Hermitian Hamiltonian, if you remember, when we unfold the equation. But if it's a Hermitian Lindblad operator, this term vanishes completely. Right? You can see that if it's Hermitian or anti-Hermitian, and this here is the imaginary part of this is just 0. So that's sort of what's called, I guess, dissipation-free or purely decohering Lindblad operators. But there are many other examples, and let me just give you a very simple example of something here that's neither Hamiltonian nor a gradient flow. That would be if you have a 4D phase space, so Q1 and P2. It's very simple, and if you only have Lindblad dynamics, this is the dynamics, and you can scribble a bit and try if you don't believe it. This is neither a Hamiltonian flow nor a gradient flow. It's a mixture of both. Okay, so it's not. Let's not dwell on this. Let me just show you an example. No, sorry. I first want to dwell a little bit on the connection to non-Hermitian. Okay, so I will go about 1 minute over time, I'm afraid. I do want to say this. So the non-Hermitian, now I wrote it again for you. I hadn't written it in this form with the G earlier, but just for comparison. So for a non-Hermitian Hamiltonian, this is the structure we get. For Lindblad, this is the structure. And what is actually sort of surprising to me, at least, is that, you know, we did say Lindblad is kind of non-Hermitian plus stochastics. It's not at all obvious for me how, obviously, it's a different thing you're approximating. You're approximating a pure state here with a Wigner function and a mixed state here, but it's quite interesting how this whole influence of the metric that was so important in the non-Hermitian one doesn't appear here. It's not, here you don't have that. You have a gradient flow up here sometimes, but the shape never feeds back into it. So it's quite interesting. I mean, obviously they do work together, and we've been checking with another connection between them that in fact, using this result here, we can reproduce this result. So, but they're kind of surprisingly different in the sense that the Lindblad does not have this shape dependence. Right, let me end with a quick example leading into, I think, some discussions later on. So I want to show you the example of a Bose-Hubbard Hamiltonian many-particle lattice system where you just have hopping between different sides and you have bosons on there and they feel each other if they're in the same side. Okay? So it's a very simple model of many-particle physics. And if we apply the Gaussian approximation to this model, so this is like using a Glauber coherent state for the system, which is not a fixed particle state. So for those of you who know what I'm talking about, you know what I'm talking about. The others, probably it doesn't really matter. But if you do that, you actually get the famous mean field approximation out, and you go a bit beyond that. So what you get is a complex Gauss-Pitievsky equation, and it depends obviously on what the Lindblad operators are exactly here, on what happens here. And you also get an information about the covariance matrix, though. That's a bit more than you get in normal mean field approximation. So let me show you a quick example, 2 modes with losses, but here actually I take 2 particle losses, so particles get lost if they're scattering together. You get this mean field dynamics with a nonlinear dissipative term, but you also get an approximation for the first order correlation function, which tells you several examples. So let me just flesh up this example here for a small loss rate of particles where we compare full quantum and classical or Gaussian approximation for the population in these 2 wells. The total population goes down, of course, and the covariance, the phase correlation we compare here to, it works sort of nicely. Obviously, it doesn't work nicely in many other places where quantum effects are important. Right, I've stretched the patience of the chair. So let me just show you my summary slide. I think I've actually said it all. So let me just thank you for your attention.
Thank you very much for this nice talk that would have need a little bit more time. Okay. So are there questions?